Hello, my name is Lee, who took on the review this time. This topic is about convection. The convection is divided into two categories. The first is free convection, and the other is forced convection. Let's take a look at free convection first. There are two examples of free convection. The first is Rayleigh-Bénard convection, and the other is an example of a simple cavity shape. Both examples are not due to the momentum of the flow from outside. Purely, it is a flow phenomenon caused by temperature difference and density difference. There are four ways to analyze a phenomenon in fluid mechanics: differential, finite control volume, dimensional, and order of magnitude analysis H. When applying the first method using the Boltzmann approximations learned earlier, so we can get the above governing equation with the buoyancy term added. If you want to solve the full flow field, you can solve the above equation using numerical analysis technique, but it doesn't look easy. So what if you want to interpret this flow qualitatively? Then dimensional analysis is performed to find out the dimensionless number that dominates a phenomenon. When applying Buckingham pi theorem based on the Rayleigh-Bénard convection phenomenon, a total of 6 variables are shown as follows. So 3 pi terms are required. The first pi term is called the Grashof number, and the second pi term is called the Prandtl number. That is, natural convection is dominated by the dimensionless number above. Next, we want to know the Reynolds number, but as you can see in figure 1, we don't know the velocity of the internal flow. So we want to know how the relationship between the Reynolds number and Grashof and Prandtl number. We are going to identify relationship between the dimensionless number, especially Reynolds and Grashof number, through order of magnitude analysis. In the first case, if the buoyancy and the inertia term are sufficiently greater than the viscous force, the previous equation would be like this equation. Then, through the series of process, the induced velocity is obtained as follows. And the Reynolds number is found to be the square root of the Grashof number. In the second case, if the buoyancy is much greater than that of inertia, the formula becomes the right as above. And the Reynolds number becomes a Grashof number. Additionally, from the energy equation, the Peckley numbers can be derived. Applying the induced velocity for each situation obtained previously, the following relationships can be obtained. And a new non-dimensional number multiplied by Grashof number and Prandtl number is named Rayleigh number. In order to understand the meaning of each dimensionless number, the qualitative meaning is indicated as below. Lastly, it can be confirmed that vorticity is also generated by free convection. If you curl Navier-Stokes equation, the following expressions appears like this equation, the equation for where the final term, this term, becomes vorticity due to free convection and is called the baroclinic torque. This term allows only compounds that do not match the direction of gravity and temperature gradient to form vorticity. Next, we will look at The first, convection. This is when buoyancy is much smaller than the inertia, and the temperature becomes a passive scalar. In this case, boundary velocity u is known, as shown in figure 2, because there exists flow outside. Thank you for listening.